Hello, everybody. Thank you for joining today's webinar entitled Defining Product Vibration Fragility. Before we start, I wanted to go over a few things. Firstly, let me just say apologies for the quality of the previous webinar's recording. We are using a new version of the GoToWebinar software, so encountered a few difficulties. Hopefully those have been ironed out and this will be smooth running, but in case there are any issues with the recording, we will rectify them before we send them out to you. So as you know, this is a Lansmont Corporation webinar. Lansmont falls under the umbrella of the Physical Properties Testers Group, or PPT for short. The PPT Group is a family of brands, all of whom are experts in the design and production of physical properties testing solutions. Sorry, Eric, can I just ask you to mute your your microphone, because we can hear some echo in the background. So let me just get on from there. The other companies within the PPT family are McMesson, James Hill, and Aluris. But if you are interested in learning more about any of our partner brands, you can visit the PPT page and see the content and on-demand webinars they have available, of which there are quite a few. So I'll put a link in the chat box shortly for you to see. I would also like to introduce your hosts for today's webinar. Eric Jonassen is our presenter for today, and my name is Sharon Smarenberg. I'm one of the organizers, and we have various support staff throughout the United States, Europe, and Asia, some of which are on the call today. Please feel free to ask questions during the webinar. You can use the question box throughout the webinar to type in any questions you may have. We will then address these questions at the end of the webinar. This webinar is going to be recorded. I know some of you have asked about it already. You will get a copy of the recording to the email that you registered with. If you want to review anything for additional clarity or pass it on to a colleague for listening or viewing, you'll be able to do that. So please don't worry about that. We usually try and make it available in the next day after the webinar, but at most 2 or 3 days. So if you've not received it at the end of the week, then please get in touch with either myself or Eric, but we should be able to give it to you shortly. Then I will also put a link to our upcoming events into the chat box for you for easy reference. But for now, that's all in terms of housekeeping. And with that, I'll turn it over to Eric for the official start of the webinar. Thank you.
Thank you, Sharon. Can you hear me now? And am I okay? There's no echo? Sorry for that.
Yes, it's absolutely fine.
Okay. All right. Apologies if that was something on my end. And I'm going to turn on my camera real quick. So I assume again that that's working. And I'm just going to introduce myself real quick and then turn my camera off, because I have a lot of video as part of my presentation, and I don't want to risk any bandwidth issues. Also, just from past presentations of some of the webinar material that I've delivered, I realize that that there can be issues with bandwidth watching some of these videos. So one way or the other, I can promise you that when we're done or I'm done, we will make sure that any of the on-demand content that we place on our website has the video overlaid in good quality as part of the recording. So thank you for your patience. Again, with that and introduction, just quickly, I've done a number of these webinars now, so I don't want to spend too much time introducing myself, but my name is Eric Jonassen. I'm the Vice President of Technology for Lansmont Corporation, longtime Lansmont employee with a fair amount of experience with shock and vibration measurement and shock and vibration testing. And so I am speaking, more from the applications side of things as I present these webinars in my experiences in both of those areas, from the measurement side of things to the testing, and even how some of this data is used in things like designing optimized packaging solutions. So I'm going to go ahead and turn my camera off now, and so I can again save bandwidth and start the presentation. Thanks, and talk to you at the end with questions. Okay, so I'm going to talk about defining product vibration fragility. Last time I presented, we talked about product fragility from the shock side of things, and I always kind of start my presentations with this simple formula. I'm not going to go any more detail than just this kind of formula or fundamental that basically says product durability plus protective packaging have to work together to overcome all the bad things that can happen in the supply chain or the distribution environment, which basically means shock and vibration, all the dynamic things in the environment. So I'm continuing today to talk about product durability. We've talked about environment in the past, and we will talk about packaging and selection of packaging materials in the next webinars. But I'm talking about product fragility today from the vibration perspective. When I say vibration, what does that basically mean? Why do we care about it? And it's because basically anytime a product or a packaged product is moving through the supply chain, it's going to experience vibration one way or the other. It doesn't matter which mode, it's going to experience that. So those are the different modes, just examples of the different modes of transport, and all of those generate vibration energy, right? There's vibration energy that comes through the transport vehicles and in containers and gets transmitted into your product. So it's really important for us to understand as much as we can about that dynamic. But what is vibration? What is vibration? Like some general definitions of the dynamic itself, and how does it differentiate? How do we differentiate that dynamic as compared to shock? And so vibration can be thought of as an oscillatory motion about a reference position. Basically, think of things moving up and down, side to side, front to back, and rocking and rolling while they're moving through the environment. So it's this oscillation or this oscillatory motion that takes place. Can look something like this, and it's steady state. It means it continues for a long period of time. It basically means whenever something is moving, it's going to experience vibration, whether it's moving in a forklift, down a conveyor, in the back of a truck, on a train, even in an airplane. As it's moving, you can't avoid the fact that you're going to experience that type of energy being exposed or input into your product in that supply chain. When we talk about what the concerns are with vibration, from a shock perspective, when something experiences big shock inputs, drops, impacts, the resulting damage from those types of dynamics can be catastrophic. That basically means you're going to have structural, type of damage to either the package or the product that would be inside when that's happening in the supply chain. It's big. It's usually very noticeable from a visual perspective, but when we talk about vibration, it's a little bit different. Vibration intensities are comparably lower than shock or impact acceleration intensities. But because it happens for long periods of time, it causes things that we would say are cumulative fatigue. They cause things to wear, they cause things to abrade, and they cause things like fitting and fasteners to potentially loosen and back out of their holding configurations. So it's longer term kind of cumulative fatigue issues that arise from vibration that cause, again, damage like wear and tear, abrasion, and these loosening of fittings and fasteners. And sometimes it's not so visibly evident, and it takes a different level of inspection to be able to identify those issues. We describe vibration in terms of its amplitude, meaning how severe it is from the acceleration perspective. We define vibration intensity typically in terms of either direct acceleration levels or something called GRMS, which basically means acceleration from a root mean square perspective. And we define vibration in terms of its frequency in hertz. And then lastly, two different types of vibration. Today I'm going to talk mostly about sine vibration, sinusoidal vibration. But we also describe vibration in our testing world in terms of random vibration. And I'll differentiate between the two as I move forward here. So this is what sine vibration looks like. Sinusoidal vibration, that's basically a sine wave of a very specific discrete frequency. And it's, you know, what you can imagine, up and down. You see the sinusoidal pattern, it's repetitive. And that motion we can replicate or simulate in the lab on a vibration test system, but that motion really does not occur like that, that discretely in, let's say, the transport world or the transport environment. You might see bits and pieces of that, but it's really for us used more as an engineering tool. If we're going to use what's called sinusoidal vibration, we use that in the test lab as an engineering tool versus using it to simulate anything in the real world. In the real transport world, vibration looks more like this. It's a messier signal. It's noisy, and it's, and quite frankly, vibration in the real world, in the transport world, is noise. You can think of noise, you know, that you hear with your ears. Noise is vibration, or sound is vibration, and it's just a different kind of a frequency range or bandwidth that we talk about when we measure it from the transport world versus what we hear. But it's noisy. That's what the signals look like, and so we have to try to make sense of what that signal looks like. But we use that information that we get from that noisy signals to create things like I'm showing on the screen right now, which are test profiles that are used to simulate different environments. And so I'm just giving some, you know, quick examples of some data profiles that are in ISTA's archives. This 4AB data depot that talk about what does a long-haul truck look like that's using parcel delivery. What does a delivery van look like? What is a steel spring truck, an air ride truck, maybe a truck in China, maybe a truck in India, maybe rail cars in Europe. We use a summation basically of all that noise that we record from the real world and come up with these test profiles that simulate those environments. So how we go from that signal to the test profile, basically, if we dissect this signal, this type of signal, we can, through computer analysis, basically doing a type of FFT or filtering of that data, we can pull out from those types of signals all the sinusoidal content that makes up that top signal. So I'm going to turn on my highlighter, so hopefully this is a little bit easier to see. But if you look at this top signal, which is, think of as more like noise or real world signal that you might measure out in the supply chain, that signal is made up of some of this 2 hertz signal, some of this 4 hertz signal, some of this 10 hertz, some of this 20, 60, 100 hertz. All these different types of sinusoidal vibration content are evident in that signal. And so computers, basically, you know, their proper analysis is able to look at that messy signal and pull all of this content that you see down below here from that to basically build these types of summary profiles. So when we look at this signal, if I show those same signals, we can say, that top waveform that I'm looking at here, the 2 hertz content, basically is a summary of that 2 hertz content we use to create a breakpoint in our PSD profile that simulates air ride transport. We also can do the same thing for the 4 hertz content, from the 10 hertz content, for the 20, the 60, and the 100 hertz. So basically, we pull, again, and do the statistical kind of analysis on real world data, dissect, looking at different filters, basically, of frequency bandwidth filters, to say, what does the 2 hertz look like? What does the 10, the 2, the 4, the 10, the 20, the 60, and the 100 hertz? What do those different types of inputs look like? And we plot them on one of these PSD profiles. Why are there kind of, at these high points here versus maybe low points here? But obviously, when we look at these kind of plots, the y-axis is intensity. So why is there a higher type of input here versus down here? Well, that's because that, in this case, an air ride truck transport, these are the airbags. This is the suspension underneath a vehicle, and that's where you see big input at that specific frequency. It's related to the suspension of the truck. Well, what about the next little bump? Well, that next little bump is related to input from the tires. From the tires, the rotation of the tires or the wheels as they spin at different speeds. You see very specific types of higher input or comparably higher input at that frequency range. And then even at the higher frequency range where there's another peak, that's you can relate more to the structural rigid body members of a transport vehicle, like a truck trailer, either the underneath the frame of the structure, the side walls, everything that goes to hold that trailer together, rattles, has basically rattles or responds to input as it's moving down the road. And you see that type of input at that frequency range. Why do we care about all those sinusoidal frequencies? Well, because components and products respond. They get excited by those different frequencies, and they all get excited differently. This is a simple, just kind of showing a beam that's resonating on a vibration table, but the video on the right is actually a video of a inside of a piece of very expensive test equipment that's being tested on a vibration system. I'll play it now, and you can see for yourself how much, just get an idea of how much different bits and pieces of tubing and hardware inside here move in response to a vibration test input. So all those pieces inside are shaking, they're resonating basically at, in this case, a specific frequency. And so it's important for us to understand at what frequencies these different pieces and components get excited and how excited they get from an overall amplitude perspective. So we want to know what frequency they like to shake at, and we want to know at that frequency how excited do they actually get. And there's a method to how you go about making those determinations. And what we do in the laboratory, I'm going to actually show you how we go about this, but in the laboratory, we're able to generate these resonant frequency transmissibility plots. And basically when we do that, what we're trying to determine is at what frequency, which I'm showing here, the frequency at something gets excited, and the amplitude, which is we again describe in terms of what's called transmissibility. So if we shake something on a table, we put a product on a table, we move that table at a controlled amplitude. If the product or the component on the table is shaking the exact same way and amplitude as the table, it's got a 1-to-1 ratio of input, the response of the component to the table input. At some frequency, at some point, the response of that component or product is going to be greater than what the table is inputting into that product. And so that's what we're trying to identify with one of these kind of transmissibility plots, is what is the frequency where that component gets excited, and what is its overall amplitude. And this is the only real math I'm going to include in this, and it's meant just to kind of show the relationship of how you determine the natural frequency of a spring mass system. Forget all the math in there, but what it says is natural frequency, so basically is 1/2 pi times the square root of, and what K stands for is spring constant, means the stiffness of a spring, stiffness or softness, but the stiffness of a spring. G is a constant, acceleration due to gravity, and then W is the weight that would be placed on that spring. So when we think of a spring mass system, you have a spring and you have a mass. And so the spring is defined by K, and W is defined by the mass of the item. So what that basically says in that relationship, if we have bigger, heavier things on the same spring, if I increase the mass or the weight, you could expect that just in this overall, generally speaking, that the heavier something is, the lower the natural frequency would be, because I'm making a bigger number here. Conversely, if I keep the mass the same, but I change the stiffness of a spring, and I make that number bigger, stiffer, that also would raise the natural frequency, right? So in bigger the number, keeping the mass the same, this overall number value gets larger. So if the K goes up, spring constant, that means a higher natural frequency. So keep that in mind as we move forward. So here's my first kind of video of showing what that might look like as we try to determine the natural frequency of a spring mass system. What I'm showing on the screen are 3 different spring mass systems mounted to a vibration table. In each configuration, the spring, K, remains the same. But what I'm changing in this example, or what's different here, are the masses. There's a heavier mass here, there's a lighter mass here, and there's a even lighter mass in this situation. So understanding that relationship, you would expect that this spring mass system would have a lower natural frequency than this one, and this spring mass system would have a lower natural frequency as compared to this one. So now what I'm going to do is I'm going to play this video, and what you'll see and hopefully be able to hear is that the table is sweeping, meaning it's changing its frequencies over time from lower to higher frequencies, and you'll see the response of the springs as the change as a result of that. So I'm going to go ahead and play that now. So you can see that each one of those springs got excited at different frequencies and in different frequency ranges. And we're able to describe that or document that by what's are called these transmissibility plots. So with the plots on the right are something that were actually generated from a vibration test system, and they show what the individual transmissibility plots look like for each of those spring mass systems. So the first one, the heavyweight green one, had a natural frequency of 28 hertz. The middle one, 35 hertz, and the light one at 46 hertz. And so we're able to document that, and again, this demonstrates that whole relationship of K being the same for those 3 systems, but heavy mass, bigger mass, lower natural frequency. This one, middle mass, a little bit lighter, a little bit higher natural frequency. And then the very light mass, so that the lighter this or the smaller this number is, the bigger that number becomes. So that kind of shows you that, or kind of validates that whole approach there, or that whole relationship. So vibration fragility, where is it? What is a test standard in our world in packaging, designing products to be able to work in a package system that's going through the supply chain? Where is that addressed? The primary one is ASTM D3580, which stands for Standard Test Methods for Vibration, Vertical Linear Motion, Tests of Products. So it's very specific about testing of products, not packaging, but of the bare products themselves. And this is what it looks like. These are again, copyrighted documents. I can't share the whole documents, but it's actually a very simple test procedure. And the key parts of that are right here, which basically says there's 2 methods that you can use if you have access to a vibration system to defining the resonance of a product or component. One is using sinusoidal vibration, and the other is using random vibration. And I'm going to, for this presentation, focus on the sinusoidal side of things. The random is a very simple approach as well. But in terms of how you would set up a machine, it's pretty simple. You basically shake your table doing a sinusoidal sweep from 3 hertz on the low end at a constant acceleration level, G level, and you sweep to a high end frequency breakpoint of 100 hertz. You can change those depending on what the range that you really want to address from your testing perspective. But for transport world, 3 to 100 hertz is considered to be a pretty good wide dynamic frequency range, where you would really see probably the most significant inputs from any transport vehicle. So the test is pretty basic, really. It's start the table moving at 3 hertz at a constant acceleration, and then what happens over time, you change that frequency. You go from 3 hertz to 4 hertz to 5 hertz to 6 hertz, so on and so forth, all the way up to 100. And then what you're doing is you're either visually looking at what is shaking to see if you can identify an excited response of your product or component. You can use, you can hear it. Oftentimes you can hear things when they resonate, and you can use sensors, which I'll show you, basically accelerometers that would be attached to your products to measure the response when you're putting it through the sweeping inputs. This is the type of vibration. This is a vertical vibration test system. Obviously, a number of different types of vibration systems. This is a Landsmont system, pretty big one, or middle of the road for us. They can be very, as small as 23 centimeter square tables, upwards of large enough to test big, let's say, displays. From a LG, Sony, Samsung, large displays, they can be 200 centimeters square, quite frankly, if you have products that large that you can shake on these tables. So you use machines like this, and here's just going to be a video showing of what the sinusoidal input looks like. So it's going to start by just kind of showing you what the table looks like when it's moving, just for visual perspective, at 1 hertz, and then 2 hertz, and then 3, up to 5, just to show what those different frequency inputs look like. And then what I'll do is I'll go ahead and play back a whole sweep from 3 to 100 hertz in a sped up fashion, so you can get an idea what that looks like. That's a 1 hertz motion. Up and down 1 time every second. That's 2 hertz. Up and down 2 times every second, so on and so forth. Now this is playing back a complete sweep from 3 to 100 hertz, but at 5 times normal speed, just to give you an idea what's taking place. And I'm going to, if I can pause it, sorry, with my, I think was my laser pointer. What you're seeing is the white line is basically, the horizontal line is the demand, what we're asking the vibration table to do, which is a sweep from, on the left hand side, from 3 hertz all the way out to the right hand side to 100 hertz. And what this line here is what we call the demand line. That's basically saying, in this example, we want the table to shake with an intensity of a half a G of input, vibration intensity, across that whole frequency range from 3 to 100 hertz. So we sweep across that whole frequency range. And then what we're doing is, this is basically to try to show a simplified, another spring mass system on a vibration table, and we're looking at the response, basically. We're looking at the response in this case, visual. And so this is just showing what the mechanics look like from running the test. And when we run this, what's being displayed right now is what we call the control channel, or the accelerometer that's mounted to the table, that's controlling the table to do a very specific thing. So this is not indicative. There's no data right now shown on the screen to show or display what's happening with our spring mass system on the the model over here. So I'll show you that moving forward. How do we go about doing that? We use things that are called response accelerometers. This is a teeny little transducer here. PCB is the brand in this case. A little transducer that we can plug in to our control system, and then we can attach it with a cable and attach it to our spring mass system, which is what I've done here, give you an idea what that looks like. And now I have an instrumented setup that's going to allow me to measure, not just visual or not just audibly, but measure with my vibration control system or test system what that resonance is and what the amplitude is. So now, if I go ahead and play a video showing that, on the bottom right, you'll notice that the display looks different, and now it's because I'm plotting data coming from that sensor. I'm going to speed the video up just so we don't have to watch. It's a slow process, so I've speeded up here at some point 4 times. And here about 10 hertz, you see the red trace going up, and there's resonance of that beam, spring mass system. You can see how it gets excited at that frequency. And then stops. And what that plot looks like, if I expand that plot, this is what the transmissibility data looks like. So it's transmissibility over here on the y-axis, meaning the relationship of response to the table input. So it's basically response accelerometer that's on that beam divided by whatever the table was doing, and that gives you the relationship. And so we call it transmissibility. Another way of thinking of it is what's the amplification? How excited did that widget get, or that beam, during that testing? And so if I draw a line across here, which is the 1-to-1 line, that means anytime that my data would be shown on the 1-to-1 line, it basically means that the response at the beam and the table to the input, the comparison or relationship, they were the same. I'm shaking the table with this amplitude. I'm also seeing that exact same amplitude on the beam. But anytime that the signal goes above that line, that's an indication of amplification, where the beam is now getting excited at the end of that beam where the mass is. So above that 1-to-1 line, amplification. Below that line is what we call attenuation. So attenuation is actually where the energy is, that you would measure out at the end of that beam is less than being put into the to the system. And so in this case, what I'm really interested in, of course, is where is the natural frequency of that beam. In this case, I can identify that at this frequency. It was just a little bit more than 9 hertz. And if I look at the y-axis, that also says the amplification or the transmissibility was about 20 times, almost 20 times. So at that frequency, about 9.3 hertz, the end of the beam was shaking almost 20 times more than the table was inputting into the system. So that's an indication of a pretty significant amplification at that point. So there's my simple, modeled up spring mass system, a product, so again, a beam suspended, a mass suspended at the end of that beam. You can think of this, when I say beam, you can think of this as the spring constant, right? It has to do with the stiffness of this system. Instead of it being a spring, it still basically acts like a spring. It's a beam with a mass suspended off the end of it. And you saw how that shakes in the previous videos. So what could I do? If I understand this relationship again for the spring constant, what could I do if I wanted to change the natural frequency one way or the other? If I wanted to raise the natural, stiffen it up, one thing I could do, right, is I could shave some of the mass off of the end that I'm suspending. If I want something to be stiffer, if I make the mass lighter, so this number would go down, the natural frequency would go up. So that's one way to stiffen the system. Another way would be just to add a structural member, right? If I have an issue like a real product, maybe a circuit board or something in the back of a piece of equipment that's suspended like that, maybe a power supply, it might be a hard drive, any kind of component that is cantilevered or suspended. If you add a structural member, what that's doing is raising the stiffness, right? So that would make this number, the K, spring constant, stiffer, which would raise the natural frequency. So I could put a beam, another structural member here. Maybe I put another shorter one there, which is maybe less costly, simpler to do. That's another way of changing or raising the natural frequency. So in this case, what I'm doing is I removed the mass. Okay, so I'm going to show you what testing looks like doing that same sweep by removing the mass. I still have the same beam, but obviously in this case, I'm making the weight much less than what it was the first go round. And you would expect by making this number much smaller that the frequency, the natural frequency that I'm going to identify should go way up or up, right? And I guess without knowing if it's way up or just a little up, we run the test, right? And let the data speak for itself. And so that's what you're going to see now in this example. Same thing that I ran before with the mass, but now without it. And right about now, it's passing through where the natural frequency was with the big mass on the end of it, there at about 9.3 hertz. Now we're getting out to 20 hertz and beyond, and the thing still isn't, the beam isn't resonating or shaking yet. Just kind of starting to raise, you can see in the signal, and there it goes. And so what that looks like now, that same kind of plot blown up to take a look at, we've got a natural frequency now way out here at 20, 30, 40, 50, about 53 hertz. So it changed from 9.3 hertz to about 53 hertz. The amplification is still, in this case, just by chance, very high at that frequency, but by stiffening it up, by lowering the weight, we shifted the natural frequency, almost 40 hertz to the right, which in many cases is a really good scenario to shift product or component natural frequencies to higher frequencies, have that natural frequency be out high, because what we do, which is really getting more involved into the next webinar, but what we do is we use packaging materials to basically mechanically filter any of that vibration energy from getting through the materials and into the product. We want those packaging materials to resonate at a much lower frequency, and there's a process you go through for determining that. So the higher you can separate package natural frequency from component natural frequency is a good thing. So what that was video of is basically of a computer, a desktop computer that was opened up, showing the insides of a computer and circuit boards inside that computer, how responding at different frequencies. And so if I go back there, I will show you that one more time. You're seeing different resonances. So one was a long, full-size computer board card, which is you see on the left-hand side, looking at very high-speed video, and then at the top left you see the shorter circuit board resonating at a different frequency. And that might look insignificant, the amount of motion that takes place there, but remember, again, that was in slow motion. And remember, at 28 hertz, that's shaking up and down 28 times a second. At 52 hertz, it's shaking up and down 52 times every second. And this is another video just taken last week of another test similar to this, showing a circuit board inside a computer shaking at a frequency in that same ballpark. Normal video speed, and then slow down 8 times. And if you notice, not only is that board shaking, a lot of displacement going out on that board because it's cantilevered from the back plane. It's kind of hanging out there, right? So it's able to move, almost like the beam I was testing in my little model. But you see everything even on that board is, even on the back plane, even this battery, backup battery, there's things that are flexing as a result of that. And that flexing, for instance, can cause things to eventually get damaged or fail, or like solder joints, or maybe that battery, because of the flexing of the board, that battery is going to back out of its nesting position, or it's, in the connection that it's made, it might lose that connection. It might pop out, or it might just become unseated somewhat, so that the connection is no longer there for the backup to be held in place. And because of that motion, here's another kind of screw that's holding that backplane board inside the chassis. Things like these, because of that motion, can become loose and back out, and that's not atypical in a very large structure, large piece of equipment. If you're testing a piece of equipment like that in the laboratory on a vibration system, what you can recognize is, what you might see during a 1 to 3 hour test is parts are falling out of that product onto the table itself, almost like it's raining parts. And that's because all those parts, fittings, and fasteners are responding to the vibration, resonating, loosening, backing up, and eventually falling out. So as we approach the next webinar, what the point is, okay, so that's great. I understand all that. I identify those natural frequencies, but why do I care about that? Well, what we do moving forward is, once we understand what those kind of responses look like, what is the natural frequency that I need to be concerned about? And there's kind of a method to the madness of, if I have multiple natural frequencies inside my product, I'm most concerned at what is the component within that product that has the lowest natural frequency, because I'm going to use packaging to either mitigate, filter, attenuate, or dampen that energy from ever making it to that component. And so this little graph on the right-hand side is, let's just say I've identified my product, and again, I will go into much more detail on the next webinar about this, but if I identify a critical natural frequency of my product, I'm going to call this like 52 hertz in this example. Well, if I understand what my package natural frequency is, so that's what I'm kind of trying to show or communicate here, which would be, let's say in the example on the left, that's my packaging going into its natural frequency. And what happens when packaging materials go into natural frequency is, remember, that's the 1-to-1 ratio of response to input. So yeah, my package goes into resonance at, say, in this example, 9.3 hertz. Forget the product. In this case, it's representing a package. But what happens below the 1-to-1 line is what we call attenuation. So that means once things go into resonance, they drop down at higher frequencies into that attenuation zone. And that basically means is they respond less. The packaging materials respond less than the input that's being put into them. Basically, they're filtering. They're acting as mechanical filters, not allowing energy through those packaging materials and into whatever is inside that package or the product. So the ideal scenario is something like this. If the left-hand red graph is a package natural frequency, and the right-hand side is a product natural frequency, you note at the product natural frequency at 52 hertz, the amount of energy that's being allowed in through the packaging material is way down here off the chart, so to speak. And that's the perfect kind of scenario, is that we want packaging materials to filter or reduce. They can never eliminate completely, but we want them to reduce, dampen, attenuate all that energy, so that at that frequency where the product has a natural frequency or gets excited, we're not allowing energy in, or we're letting the least amount possible in through the packaging to excite that component. And that's what we'll talk about more as we move forward into the next webinar, which is scheduled for Tuesday, October 24th, is really, all right, let's talk about how we define those types of cushioning and mitigation properties from packaging material perspective. So I wanted to just point that out, that we'll get more into that detail next go round. And with that, I will say thank you and take some time now to call Sharon back in, and if anybody has any questions, be happy to try to answer. Thank you very much.
Thanks, Eric. If anybody has any questions, sorry, Eric, there's an echo again from from my sound. If anybody has any questions, please take the time now to put it in the questions box, and we will see how many questions we can get to. The first question that we've got available, Eric, is should we attach the vibration sensor onto the fixture or onto the DUT?
Maybe you mute while I'll go on and off as I answer. So hopefully the echo's not there for everybody else. Apologies if it is. But the accelerometers can be very, they can range in size and mass, so that you can get very small response accelerometers that can be used to be placed on the DUT. So typically you want your accelerometer, your control accelerometer that's measuring the input, to be relatively close to whatever it is that you're testing. For us, on our big tables, sometimes it's not practical to have what we call the control accelerometer on top of the table, because you have a big product or something mounted to the table itself. But that's the control accelerometer is giving you data that's representative of what's going into the product. Then you want, again, another accelerometer or sensor to be on the DUT somewhere, or whatever the critical component. Typically, it depends on how complicated or sophisticated, complex your products are. But sometimes you might have multiple sensors placed around your product, or you move that one. If you only have one response accelerometer, you might move that around your product to identify different areas of concern on your product that you want to understand, or that you're concerned about, that they might be shaking too much or getting too excited from that input vibration. So it's important to the location of both. You want to, again, you want to know what's going into the product. So that's your control accelerometer, and that can be placed right, on the tabletop or close to wherever the product is. But then you want a different sensor that would be placed on the DUT or the component that you're trying to understand its response. Don't know if that makes sense or not. And again, if it wasn't clear, please feel free to email me, and happy to try to explain answer or address that question more thoroughly.
Thanks, Eric. Next question. So for a complex system like a desktop computer, for example, what is the general guidance for picking locations to monitor response acceleration? What do you do if you have a lot of potentially sensitive components?
Yeah, well, I'm more from the equipment testing side of things, so I think the better people to answer that question are the people that manufacture those products. But what I would say is they typically There's a history, right, involved with products. Usually it's not, someone doesn't bring an absolutely brand new product, maybe design to the table without some historical experience with similar products. Might still be different, but similar types of products, technologies, and so the product might be different, but the components in those products often aren't. So what I would say is from my experience is a lot of reliability engineers or product engineers know going into the test or a new vibration test, they have an idea of what's areas of concern. Again, if it's hard drive, power supply, display, there's some history associated with it that says we always have problems or we always have concerns in this area. And so they aren't starting from absolute scratch or don't know what to do. They usually are focused in certain areas because there's some historical information or precedent based upon that. So they'll focus. It still might take a number of different sensors in those areas. And yes, again, what is what's of concern? There's different ways of addressing resonances, input. So you can never get rid of the input, right, from vehicles, but you're going to have responses. And so the different ways there's a couple ways of addressing how to mitigate that. One is to fix the product or address the product, like I kind of showed. You can tighten things up. You can add fittings and fasteners. You can add some kind of a structural member, straps, literally fasteners to tie things down. Or if that's not an option, people do it with packaging materials. There's ways to then use packaging materials to lessen the amount of energy that gets to that sensitive item. In generally speaking, it makes better sense from our perspective to improve the product itself and not rely on packaging materials, because if you can make the product more durable and more robust, then that's better value that's left with whoever the consumer is, the purchaser of that good, that product, instead of addressing it from the packaging perspective, where packaging might be, it might be expendable packaging that's being used that ends up being thrown away or into a landfill, even if it's recycled. If you can fix it by making the product better outcomes typically for everybody in that case. I'm going back on mute, sorry.
Thanks, Eric. Just in relation to the previous question, can you just quickly explain what DUT means?
Device under test is usually what that means. It's the test item, test article, which again can be a number of different things, but it's, since we're talking about products, I would say it's either the product that's being tested or, oftentimes what's being tested are subcomponents of a product. It's not just necessarily a big product or a full computer. Sometimes it is, but sometimes people put the main components of a system on the test table, test equipment itself to test. So device under test.
Thanks. Sometimes I hear of Q as being defined as the aspect ratio of a peak's height over width above its 3 dB level. Can you please clarify?
Yeah, I would agree with that. Q is another way. Some people use Q synonymously with or replacing with amplification or transmissibility, but Q has a much more defined or refined definition. So it does have to do with, when you look at those plots that I was generating from my measurements, there are different, they're either sharp peaks, they're very well defined. When it goes into resonance, the table is moving across and goes, when it hits a resonance, it goes sharply up and sharply down into attenuation. Some other ones are more rounded like this, more gentle. And so the Q is defined more based upon those signatures, that speak to the discreteness of the resonance. versus the broadness of the amplification zone. So we call the zone, if it's a sharp signature to it on the approach and the decay, that's a narrow band of amplification. But if it's also more, or conversely, if it's more rounded, the amplification zone is broader, harder thing to address, quite frankly, if it's a very broad amplification zone with packaging materials, because they have to work across a wider frequency range to try to mitigate all that energy from getting through. So the Q does speak to the range, or the broadness of that amplification zone, the relationship of the peak to the zone.
Thanks, Eric. So the next question, do you test at higher frequencies than 100 Hertz on your hydraulic system, like the next on electrodynamic shakers?
Yeah, so hydraulic shakers or Landsmont, and the people that we would like Landsmont, or maybe that we would compete with, we use hydraulics because we're focused more on the low frequency range. When I say low frequency, that means anywhere from like 2 to 200 Hertz. Actually, we can go 2 to 500 Hertz with our systems, depending on how they're configured. But when you look at the energy that's present primarily in the transport world, or the distribution side of things, so the energy that you would see in a truck, in a train, in an airplane, intermodal containers while they're moving, that energy, if you're looking with data acquisition from the real world, you can record out to 5,000 Hertz if you want to. But what you'll notice is that that the energy of significance occurs primarily in, once we get above 100 Hertz in any of those modes of transport, the energy drops off significantly. And why is that? Well, because if you think of a truck, trailer, a train, boxcar, intermodal, well car, an airplane, a ship, they're big items, right? And remember what, even in that spring constant relationship that I showed for a spring mass system, the bigger, the heavier a mass, the bigger it is, the less it can respond, the lower its natural frequency is, the lower it can respond. So we don't see a lot of high amplitude energy, and that's why most of the vibration systems that are used to simulate transport are focused more on that lower frequency bandwidth. And we go down to, with hydraulics, you can get down to the 1 to 2 Hertz on the low end. Why is that? That's because we, to simulate those big inputs, meaning big displacements that you would see from a truck trailer, from a rail car suspension, and that's big energy, big displacement that can cause, let's say, packaged products or a unit load to be thrown around, to be moved, right? Move up and down, side to side, while it's in transport. And so you need large displacement. Typically, or generally speaking, electrodynamic shakers don't have that stroke. So hydraulics are used for simulating the transport environment. Electrodynamic shakers are used more for testing, like reliability testing, components, smaller items that are really testing things with the intent to take them to define their almost their failure criteria, their durability, reliability tests. Not so as much focused on the transport world, which is what hydraulics are used for. And there is some crossover there, but so just broadly speaking, hydraulics used to simulate transport because of large displacements. Electrodynamic used to do reliability testing out to really high frequencies, just to kind of almost test things to failure, see if you can cause things to fail from a vibration perspective.
Thanks for that, Eric. I don't see any more questions in the question box, but I have just put Eric's email address in the chat box, and obviously it's on the screen. So please feel free to reach out to Eric if you have any further questions that you'd like to discuss. Again, thank you so much for joining us today. We hope that you'll join us for the next installment in the webinar series, and it is cushioning material selection and transport packaging design, and that will take place on October 24th, as Eric said. But for now, thank you very much. We are going to end the webinar now, and we hope to see you for the next one.
Thank you very much. Thanks for your help again, Sharon. Appreciate it. And we'll get the video recording placed soon with good quality videos. Have a good day, everyone.
Thanks, everybody.